Every piece of data you generate, every text, search, and click, starts as a meaningless quantity floating chaotically in the digital void. Without organization, a system drowning in this raw data is incapable of producing any usable information. Software algorithms cannot function in that chaos. To process information, developers must physically allocate memory, organizing those raw quantities into strict, predictable structures. The fundamental building block for this organization is the node. By splitting it into two parts, a node can hold a specific piece of data on one side, while the other acts as a pointer, directing traffic to the next destination in the system. When we string these individual nodes together, we create data structures. These are the architectural blueprints that dictate exactly how data is stored, retrieved, and modified. These blueprints define the active laws of digital physics. Selecting the right structure ensures an application scales to millions of users, while a poor choice creates a performance bottleneck that can crash the entire system. This diagram shows the primary classification of data structures, splitting into linear and nonlinear pathways. As the comparison chart details, linear structures arrange elements sequentially for a single run, while nonlinear structures branch into multiple levels. However, a structure is also defined by how we interact with it, specifically through operations like traversing, inserting, deleting, searching, and sorting data. To manage these interactions, we use an abstract data type, or ADT. This acts as a control panel, using data abstraction to hide the complex background code while exposing the essential operations needed to manipulate the information. This graph shows why choosing the right structure requires a strict efficiency trade-off. We measure this using big O notation. A flat O1 line indicates instant constant performance, while an exponential curve reveals a massive drop in efficiency as the volume of data grows. Building a reliable system means matching the data structure to the expected growth and operation frequency to avoid these performance bottlenecks. We can see these rules in linear traffic. Standard arrays require a fixed size allocated up front. If the array shrinks, memory is wasted. If it overfills, the system fails. To solve this, developers use the singly linked list. Since each node contains its own pointer, memory blocks can be scattered across the system, relying on single directional arrows to form a continuous chain. This flexibility allows for instant insertion and deletion without resizing the structure, but it comes with a penalty. Finding a specific item requires a slow search, checking every node from the beginning of the chain until the target is found. The structure can be modified to handle different traffic needs. A circular linked list loops the tail back to the head to avoid dead ends, while a doubly linked list adds a second pointer to every node, allowing for two-way traffic. While linked lists overcome the physical constraints of rigid memory allocation, their sequential traversal rule makes them inefficient for any application requiring fast, random access lookups. Other digital operations require absolute restriction rather than flexible access. A stack operates under the law of LIFO, last in, first out. By restricting all data entry and removal to a single vertical endpoint, the newest piece of information is always the first to be processed. The ADT handles this through three commands: push to add an item, pop to remove it, and peek to view the top. These rules prevent errors during tasks like tracking browser history, where the last page visited is the first one returned. If a process requires fairness instead of recency, we use the queue protocol. This creates a one-way traffic lane based on the law of FIFO, first in, first out. In a queue, data is added at the rear and removed from the front. This provides the logic for scheduling printer tasks or managing data packets for a multiplayer server. Stacks and queues trade away the freedom to search any node for the absolute predictability of processing data in a required order. When we look at the broader digital landscape, it's clear that complex algorithms are entirely dependent on these organized pathways. Lists, stacks, and queues provide the underlying architecture that keeps information flowing flawlessly. The core of digital architecture is matching these physical constraints to the functional goal of the software. Navigating these trade-offs is where the transition happens from writing simple code to architecting systems designed for efficiency and scale. Keep building your knowledge one concept at a time.